as we continue to look at this relationship between a function, its zeros, and its factors, in this example, we're going to go backwards. We're going to go backwards, and we're going to start with the zeros. Remember, those are the numbers that when I plug it in would make it equal 0. And I want to go back to the factors, which have some sort of x's, and then take my factors and put them together into my function, because the factors are the building blocks from one step to the other. So I'm going to go backwards, use the ZPP, zero product property, a little bit backwards. There's a couple ways to do this. You can just do it visually and say, hey, if I get an x equals -3, it had to come from an x plus 3. That's one way of doing it. Another way is you just pretty much unsolve this, maybe if that's a way of saying it. I just add the 3 over, and I get x plus 3 equals 0. That's another way of doing it. So when I come over here, you could subtract the 7 over and get x minus 7. Or just think what would give me a 7 when I set it equal to 0. It would be x minus 7. When you get to these, it's a little bit trickier because I don't want to have fractions. I don't want to use x minus 1/4. So you can think of it a couple ways. You can just cross multiply the 4 up, get 4x equals 1, and then subtract the 1. So it's 4x minus 1. Or you can just take this 4x minus 1 and just play with it a little bit, put a 4x plus 1 or minus 1, and then see which one would give you the 1/4 as you go backwards. Here, I could take the negative and the 3 together. Just the 3, and bring him over as a 3x, and that would equal -5, and then add the 5 over and get 3x plus 5. Just play around with those a little bit, and you'll be able to see eventually what factors give you these zeros. And then when I go back to my original, all I do is just take all of my building blocks, all of these, and put them together. So x plus 3 times x minus 7 times 4x minus 1 times 3x plus 5. It's a pretty big function. It has 4 different linear binomial factors. Lots of pieces to it if we were to FOIL that all out. I'm not going to, but I'm still going to be able to tell what the degree, leading coefficient, and constant are. Degree, just like we did before, I have a first power here, 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 and here. So the degree is going to be a 4th power, 4-degree polynomial. It's going to be a quartic function, which already tells me something about the end behavior. They're going to be the same end behavior. Leading coefficient, again, I'm just worried about positive or negative in this case. So if I look at all of these multiplied together, they're all positives. So the leading coefficient is going to be positive. So I know that my end behavior will be up, up. And lastly, for the constant term, you can, in this case, just multiply together all of these values. And in a little bit here, I'm going to give you another way of doing it. You can also just plug a 0 in for all the x's. That's another way to get the constant. Just put a 0 in for all the x's. So if I take 3 times -7 times -1 times 5, the constant term is a positive 105. So there's my set of degree, leading coefficient, and constant. But more importantly is going backwards from the zeros up here to the linear factors. One more term that we have to introduce here is what's called multiplicity. For multiplicity, I'm just going to simply define that as how many times we count each factor or 0/root. I'm going to use those terms pretty interchangeably here because there's that relationship between them. So how many times we count each factor or 0 or root. So if I come down here to p of x, I'm going to go ahead and break off the linear factors. So the most obvious linear factor to me here is just this x minus 1, so he goes there. I also see this 5x plus 7. So let's look at those two first, then I'll get the other one. The x minus 1 has a degree of 1. So when I look at his 0, remember linear factors have x's, zeros are numbers. I set x minus 1 equal to 0, I get 1. And his multiplicity is also going to be 1. because that's the power up here on his linear factor. For the 5x plus 7, I get negative 7/5. Remember, I'm just taking 5x plus 7 equals 0 and solving it. But his multiplicity is going to be 3. There were 3 of him. We didn't write all 3 out. We just tried to compact that down a little bit. But he is to the 3rd power, so his multiplicity is 3. The last one's a little harder to see. The linear factor is actually just x. Again, I don't care about the negative 2. The negative 2 is just chilling out there. He's going to be just some sort of scalar. He's just making everything twice as big and reflecting it. But I have a linear factor of x, which means his 0 is 0, because it's x equals 0. But he has a multiplicity of 2. We're going to count him twice. So multiplicities are just saying how many times I count the 0 or the factor. In terms of degree, leading coefficient, and constant, the degree up here for this one is going to be, I have 2, 1, and a 3, so that's looking like it's a degree 6. Leading coefficient, I just take the negative 2 times a 1 times a 5, 3 times, so 5 times 5 times 5 times 1 times negative 2. All that matters is that he's negative. I think he's negative 250 specifically, but all that matters is he's negative. And the constant, this is the one that always trips people up. They want to just multiply these two values together up here, the negative 1 and the 7. But up above I mentioned that you can just plug in a 0 for x. So doing that here gives you a little better idea of what it is. If you put a 0 in for all the x's, you're actually going to get a 0 out for the constant term, which is kind of weird, but if you think about it, to FOIL out these last two binomials and then send an x squared through, everybody's going to have at least an x squared or higher. So the constant 0. There's nothing without an x. Example 2. Example 2. Given the zeros and multiplicities, create the factored form of a function b of x that has a leading coefficient of 90. So we're going to go backwards, and we're going to throw this extra little twist in at the end. We'll leave that leading coefficient of 90 for later. So let's go backwards from zeros to linear factors. So we're going from numbers to something that has x's. Numbers to something that has x's. So as I go backwards here, again, you could subtract the 1 over and get x minus 1. Here it's going to be x plus 2. This one will end up being 5x minus 3. Bring the 5 up and then subtract the 3 over. This will be 9x plus 4. However you get those doesn't matter to me, as long as you get those accurately. I'm just going to put the multiplicities in with them and leave a little room here at the beginning. I need an x minus 1 to the 3rd power because he has a multiplicity of 3. The x plus 2 has a multiplicity of 2. The 5x minus 3 has a multiplicity of 1, so he has a power of 1. And the 9x plus 4 is just chilling there. So at this point, I look at it and I'm saying, okay, I have all of my factors, all of my pieces. I just need to make sure that he has the correct leading coefficient. So if I look at my coefficient right now, my leading coefficient, he is, let's see, 5 times 9, and then there's a whole lot of 1s with these two. So 5 times 9 gives me 45. The problem is 45 isn't what I'm supposed to have with 90, and that's where that scalar out front comes in. I said you just multiply by that number. He matters, but he doesn't matter for the zeros. Now he does for the leading coefficient. So if I stick a 2 out front, if I take 2 times 5 times 9, that's going to give me 90. Or I could have just taken the 90 and divided by what I already have, the 45, and that would have given me my answer. So you just have to be careful that you get this scalar out here correct whenever you have extra information like that right there in the problem. So in this one we went backwards, we added in these multiplicities, and we made sure that we had the correct leading coefficient. Lastly, example 3 down here, I'm going to take this information and create the function and make sure that he has this leading coefficient of 8. So if I look at it, I can create like a little chart over here of zeros and what I'm going to call LF, linear factors. So if he has a 0 of 6, we've seen that that linear factor had to be x minus 6. Zeros are numbers, linear factors have x's. So I know he has an x minus 6, and it's all raised to the third power because of that multiplicity of 3. If I have a negative 3 halves, we're doing the same thing from up above, just with a little less structure. He becomes 2x plus 3. And again, you just have to kind of sit and look at that a little bit, make sure you get it right in your head or write it out. However it is, it doesn't matter as long as you get it appropriately, the 2x plus 3, and a multiplicity of 1, so I don't have to write it. Now I'm going to check my leading coefficient to see if I'm correct. In this case, a leading coefficient of 8 is what I want, right there. But I only have a leading coefficient of 2, so I have to put that 4 out front, just to scale my graph a little bit, make him a little bit larger. So there's my function. I've gone through and I've taken care of that piece, and that piece. So hopefully now you have a better understanding of how linear factors and zeros relate to the function, specifically when I introduce multiplicities.